That was a talk on fire. I cannot match this energy. Much shorter talk and in slower pace, really. This is about creep, right? And 7 minutes for creep is not much. And this is funded on a short-term project as well. I need to acknowledge collaborators, Andre Barbosa, Ben Jawang, and Desi Tibebu, our postdoc, working on this one. The topic is about developing efficient test methods for rolling shear creep characteristics in cross-laminated timber. Now, rolling shear, you can load wood in in very many ways, except this one, shear perpendicular to the grain. It's actually you don't see it. You cannot do it. You cannot really take scissors and cut wood. But this would be like rolling shear would be rolling perpendicular to the longitudinal axis in tangential radial or radial tangential plane. So this to bring it home. Why is this important? Because it has not been important in structures for a long time until the cross-laminated timber, when we started putting the pieces that are oriented crosswise into structural members. And then as you bend these members, something happens with these transverse layers, and that's rolling shear, okay? So now in static, it's a immediate thing. You just, elastic deformation happens immediately, but when you leave it loaded that way for longer, you trigger creep, which is like the long-term deformation. Let me skip essentially I said what I put on the textual format in here. So now there are ways in engineering to accommodate, to calculate how much of the deflection in beams, in static and in creep, could theoretically come out of this rolling shear. How much does it contribute in here? The problem is that the methods, the shear analogy method is based on rather skimmed data. And if we scratch this data, they come back. Let me do this in the interest of time. We go back to Wood Handbook, right, where there are some data published on what the shear modulus in the transverse direction is. This takes us back to Josef Bodik, celebrated person who did not do this research. He refers back to Herman and Patton. This is 1948 research, right? And then they reflect to earlier research who say, well, we just think that the proportion between the elastic and shear modulus can be like this way or that way based on this cloud of. We are far from being certain of what happens in there, right? So that's the point. Now, the little new testing that is happening is rather complicated. It's very difficult to isolate shear from other types of loading. So even here you have a combination. These are colleagues of mine in Linnaeus University in Sweden are doing things like this. You have to combine it with a little bit of compression, right? So then separating what is the effect of compression versus what is the effect of shear is rather difficult. This little bit of creep that they did, it's like 60 minutes for creep, right? But even in the 60 minutes, they see a lot, and the effect of moisture content for this. So if you think about it, this is like in creep, timing in seconds is like unheard of. But even in this very short period of time, the deformations can double. Ooh. And then if you try to express it in terms of the effect of moisture content, effect of moisture content on this creep is rather substantial. And this is on the very short time frame in here, right? And if you think of what would be the equivalent shear modulus after the period of time, it just declines rapidly. And with this being very far from the published about 500 based on this body engine, based on this Harman pattern publication. The shear modulus will be in transverse direction will be about 500 megapascals. It's like 50 megapascals. I don't think we are incorporating this in our design procedures, right? So this is what motivates this thing. We would like to know more about it. Now, one of the ways of having shear isolated from other types of stress is in torsion. And it's like in circular shafts, isotropic shafts, this is like known thing. So here would be different components of stress being seen in the shafts. You see actually only this one being active in here. That's easy. People are trying to replicate it with wood in now transverse direction to replicate shear wood, and it's rather a nightmare. I mean, you could do it, but just the level of machining in here and the outcomes that you have are not really conducive for large scale testing, and particularly not for creep. Similar tests being done on the adhesive bonds. It's not quite the same thing. We were trying similar thing with a small, this is our device, right? Way back 12 years ago or something, motivated by what is the capacity of the adhesive bond in shear and so on. Now we thought, this wasn't particularly successful, but we can reuse the same apparatus for creep. Now the apparatus looks like the piece, the CLT specimen, and you can actually build longer specimen as a shaft, right? Being put in between two clamps, mechanically locked, loaded with a little lever in here. And now instead of putting this in the testing machine, we would like to put it in with some dead load. Now, the problem is, do we understand what happens in this piece of a material? As we load it that way, when it's the transverse, when it's orthotropic material and put in the transverse direction to the action of the axis of the torque. And we did some measurements using digital image correlation. You see two faces visible to the camera over there. And this is what we guess material point method. If this slide looks dated, it is. I mean, 12 years ago, right? This is how it would look like in a rectangular shaft that is orthotropic. And this is what we measure with the IC. So now if we look at the surface, this would be outcome of this modeling that we've done before, but just the strains on the surface. And this is what we measure. I think we are pretty close. This gives us some confidence that we actually can translate what we see in terms just of an angle to the stress and strain state inside the samples and make a little more educated statements about it. This is how our specimens look like. We started with the same type of specimens that are being used in delamination, easy to harvest. We were forced to reduce it to smaller cross sections to induce actually the more measurable angles. So this is a pretty stiff thing. This would be easier to measure if we increase the length of the shaft. This is our first attempt at measuring angles. We are so impatient, right? We already had the apparatus and we are still searching for the sensors. But these days we have this kind of fancy sensors. They take a little bit too much space on the specimen. So now our effective gauge for measuring the angle is reduced. We are working on this. And with this, we are testing. Now, this is creep, don't hold your breath. We've went through 6 specimens, out of which this is on the only second one that actually creeps rather than breaks within an hour or two or during the loading. The torque that we put on it is pretty substantial. This is by design. We want our results quickly as far as creep is considered. And this is, as I said, don't hold your breath. This is where we are, right? Actually, we are right now at the 60 days of testing of the 6th specimen. That would be it for this project. Thank you. Mm.